Wave or particle? Here we focus on what in quantum mechanics is very much a schizophrenic nature for light. Isaac Newton in the late 1600s laid out a theory of optics in which he assumed that light is consisted of particles. Christian Huygens had a different theory of light. He said, I think light is a wave. And for roughly 100 years or so, there was debate about whether light was a wave or particle. And then came along a series of experiments that were done in very early 1800s by Young, which proved conclusively that light must be a wave. Young did a very simple thing. He took some kind of barrier and he made two small holes in it, and he made those holes very close together. They don't have to be microscopically close, by the way. Some ways away from that barrier, we have a screen. What we're gonna do is to shine light at that barrier, and we're going to ask ourselves what we're gonna see on this screen. If light consisted of particles, what would happen is all the particles would be blocked except where they hit the barrier, and the light would go through, basically in straight beams, and we would see on the screen two bright spots opposite the two slits. That would be a good evidence that light consisted of beam of particles. What on the other hand happens if light consisted of waves coming in? What happens is light waves go through these slits, and each slit in sense acts as a sort of circular waves that then spread out of the slits. And you can see there is an interesting kind of pattern. There are places where waves interfere constructively when two waves crest coincide, and there are places where waves interfere destructively when waves crest and trough coincide. Therefore, in this particular case, we are going to see on the screen alternating light dark bands, and there are actual sets of interference patterns taken by putting a camera film in the place of the screen of double slit experiment. So we have a very clear experiment that shows light behaves like a wave. This experiment was first done by Young, and he concluded that light must be a wave. And then we have Maxwell coming along in the 1860s and showing us light is an electromagnetic wave. So we are very comfortable with the idea that light is a wave, and that idea figured importantly in Einstein's development of special relativity in 1905. But now we have Einstein again in the same year, 1905, saying, wait a minute, light is a particle, or at least it comes in these discrete little bundles called photons, and they are acting like little particles, like little billiard balls that can hit an electron and eject it from the metal in the photoelectric experiment. So it's Einstein who tells us light seems to be a particle. In the photoelectric effect, that explanation requires a particle nature like for light. In the double slit experiment, interference is something that happens to waves. It doesn't happen to particles. Two particles can't be in the same place at the same time. So which is it? In 1923, there was an experiment done by Compton, and it convinced any skeptics who didn't believe in Einstein's photons. And the experiment consists of basically a free electron that isn't tied very strongly to anything. It's actually tied loosely to an atom, and hitting it with very high energy photon. The photon comes, hits the electron at rest, electron goes off in one direction, and the photon bounces back. The photon gives off some of its energy to electron. The photon can't slow down, but it lowers its frequency, and the frequency is lower exactly as predicted by doing simple physics of a simple billiard ball collision between two billiard ball-like particles using relativistic mechanics. So we have a very clear evidence for particle-like behavior of light. So is light a wave or a particle? And I'm sure you love me to give you an answer. It's really a wave. It's really a particle. But I can't. The quantum mechanical answer is both. Let's look at our double slit system again. We know what happens when light goes through the both slits, but now we don't know light whether it's a wave or a particle. Which slit did each photon go through? How do the photons go through those slits and then bend themselves in such way that they would end up in the right place on the screen? If light is a particle, we have to be able to give a particle-like explanation for this phenomena. Let's block one of the slits and see if the half of the photons go through the other slits. And what happens? We see a single spot on the screen. We've destroyed the interference pattern completely. What we have tried to do here is to catch the photons in the act of behaving like particles rather than waves. And what they've done for us, they acted like particles and the wave behavior was gone. You might think you can put little detectors that sat there at each slit detecting the photons. If that thing is actually capable of detecting the photons, then it's going to disrupt them in some way and you will not get the interference pattern. If they detect the photons going through, then you find two spots on the screen just as if light was a particle. You can't do it. You can't catch it being a wave and a particle simultaneously. Let's try this one. Let's turn the intensity of light down so low, make it so dim that there is only one photon at a time in this whole apparatus. And in fact, this has been done. You can turn it down so low that sometimes once a day, one photon leaves the light source. So there is only one photon there at a time. So photons aren't somehow interfering with another. And then you would say clearly that one photon either goes through the left slit or it goes through the right slit. What is the result? And what happens if you do that? You will build up an interference pattern that looks exactly like the one that we saw before. How this happen? How could possibly individual photons create this pattern? The answer is each individual photons went through the both slits. It looks like a random process at first, but it finally emerged to the interference pattern. Somehow the individual photons know to land on the screen in a way that it eventually builds that interference pattern. What is all telling us? It's telling us that light is both a wave and a particle, and there's no way around. If you don't try to detect light, what would you always find is light acts like a wave. If you try to detect each individual photons, like build the photoelectric effect experiment, then a particle-like interaction will take place. It's wave and a particle both. Light has a dual nature. There is a statistical relationship between wave and particle aspects of light. In places where the wave is strong, you are likely to find a photon. In places where the wave is weak, low amplitude, you are not likely to find a photon. It's a probability that depends on the amplitude of wave. So there isn't really a contradiction between the particle and wave aspects of light. They are not contradictory. They are in fact, as Niels Bohr said, complementary aspects of the same reality. And Bohr elucidated a principle called principle of complementarity. You never catch light acting like both wave and particle at the same time. You'll never catch light in a contradiction. What determines which it acts like is what you choose to do with it.